All right, so the first thing that we see when we're looking at this question here isn't really necessarily the first thing that we're going to be doing. The first thing that it's saying is state whether or not it's continuous. And honestly, that's what we need to do all of our work to figure out. So don't think that like as you're reading through these directions that, okay, like I need to know right now if this is continuous. We can find out if it's continuous or not, okay? So along the way, we'll be able to find these things out. We'll be able to find out if it's removable or non-removable, okay? We'll be able to find out if it's a hole, if it's a jump, if there's a vertical asymptote, okay? And we'll have to list what values that happens. That's important to us. We need to know what values we're having these breaks in our graph, okay? So the first thing that you can always try to do is try to simplify your function, right? Try to see if you can factor something out. Try to see if you can eliminate a factor. So that's our goal always, is to try to simplify. So let's write that down. Okay, so it's a little note. Try to simplify first. Okay, and that's kind of like always, like let's just make it easier to get started with. Now for us, I really can't, right? I have just an x in my numerator. I have an x squared plus 1 in my denominator. They're not going to have a common factor. I can't break this factor up. It's not going to get broken up any further. This is just it, okay? So we can't simplify this one any further. So we can continue on from here. Okay, so if we could have simplified something, so if something would cancel out, okay, that would make a hole in your graph, or a point discontinuity. We'll write that down too. I'll do like a little second note here. Okay, if a factor does cancel, when you set that factor equal to 0 and solve, you have a point discontinuity at that x value. Okay, so we don't have that in this case, but you might at some point have a factor that cancels out. And that right there, off the bat, we know that that's going to be a hole in our graph. That's going to be a point discontinuity. And that's also what's called a removable discontinuity, because if you can just remove one point and put that one point back in, that is a removable discontinuity. Okay, but we don't have that here. So we can figure out maybe if we have a vertical asymptote. All right, so if we have a vertical asymptote, that would occur when you set your denominator equal to 0. Okay, so we'll have another little note down here. Okay, vertical asymptotes occur. Oops. When denominator equals 0. Okay, so what we would do from this point, we would just take our denominator, see if we can solve. We set it equal to 0. Subtract 1. Now, right now, you might kind of feel like you should have a vertical asymptote because we set it equal to 0, but you don't always, right? Because when I take this square root and I take the square root of both sides, will I get a value on the right-hand side? No, right? It's a negative number. So there's no value that's going to make my denominator equal to 0. So there's going to be no vertical asymptote. Okay, so this is not real. So no vertical asymptote. Okay, so when we're looking at this, again, worst case scenario, if we're stuck, right? That happens sometimes where you get stuck. You can plug this function into your calculator, or I would truly recommend Desmos. It's just a clearer and easier graph. So let's just see what this graph looks like on Desmos. Okay, maybe we tried all of our facts here and they're just not going to work. So we're going to go to Desmos. Okay, and our function was y equals x divided by x squared plus 1. Okay, and you can see here that it's continuous, right? And we were kind of onto that path with what we were seeing. If I zoom in, okay, there's no holes, there's no jumps, there's no asymptotes. If I continue this graph on forever, it will continue and I will have every single x value. So what's nice is this is a great way to double check your work before you submit it. This is continuous. Okay, so let's get rid of this. Don't know how. There we go. Okay, so that's all you really have to do is say, can I find these holes, or can I find an asymptote? And if you can, then it's definitely not continuous. For us, we couldn't find anything. We couldn't find anything wrong with it. We double checked with our graph, and we just realized that, okay, our only option now is that it must be continuous. Okay, so now again, we see the same beginning of our question is saying to state whether or not this is continuous. And if not, state what the discontinuity is, like where does it occur, if it's removable, is it a hole, a jump, or an asymptote. So we have a piecewise function. Our first thing we want to do, just like before, is that we do want to try to simplify our our functions here. So my function on the bottom is just 8, right? If that's the line y equals 8. That's actually just going to be a point because that's only at one specific x value. So the rest of the function that we're graphing is that x squared minus 9 over x minus 3. So I'm going to just do a little bit of side work to try to simplify this because in my mind it feels like I can simplify. So can I factor my numerator into anything? And when I think about it, I see an x squared minus 9, which is something squared minus something squared, right? So we're kind of leaning into this whole difference of squares here. So we have x, which is our first term squared, and 3, which would be our second term squared. Difference of squares, different signs. So we have x plus 3, x minus 3, and this is all over x minus 3. So what's interesting here is that we do have pieces of this function that will cancel out. We have these factors, x minus 3 and x minus 3. One on the top and one on the denominator. They cancel out. So this function, my whole top function now is just x plus 3. So I'm just going to write it here so that we know that this is our piece that we're using. That's what this becomes. Okay, that's just it. But something important happens at x minus 3, right? X minus 3 was what canceled out. We need to make sure that we set that equal to 0 because that's going to be a hole in our graph. Okay, so we'll do a little bit of side work. So here's our note. Since x minus 3 canceled out, we have a hole when x minus 3 equals 0. Okay, so we can solve this. So we're going to have a hole in our graph when x equals 3. Okay, so a hole in the graph, we know that that is what's considered a point discontinuity. Okay, so we kind of did our groundwork here. We did our simplification. We already found out we have a hole in the graph. Now our real idea is to figure out, okay, will we have continuity at 3? And I know it seems a little bit like we're just kind of like repeating our same ideas and terms here, but we need to go through the steps because obviously this one's going to have a hole at 3, but you're going to have other functions where they won't. So let's go through the steps that we need to take to really prove if or if not this is continuous at the value of 3. So the first thing that you always need to prove is that f of c is defined, which means that I need to be able to plug in my c value and just get a point out. So our c value was 3, right? That's the value that we're concerned with. So we're going to plug that in. And when we do, we need to be careful with our piecewise function here. Okay, you need to make sure you're plugging it into the right piece. So we're looking for when x equals 3. So obviously our two choices are here when x does not equal 3, so that's literally any other number in the world. Or here's our piece for when x equals 3. So we can figure out that f of 3 is 8. Okay, there's really no function there, so it's just f of 3. We look at our piece there. If we had any x's, we would plug in our 3, but f of 3 is 8. So it's the first piece of our answer here. The second piece that you need to find is the limit at 3. So we need to find the limit when x approaches 3 of f of x. So to do this, we need to find the left-hand side limit, the right-hand side limit, and then we need to find the limit at 3. Okay, so for us, we can see that when we're looking here, our limit at 3 is when we can plug in that value of 3. You could do your left hand and right hand, and that would be from, you know, our top function, right? Numbers to the left of 3 and numbers to the right of 3, they don't equal 3. So looking at our restriction here for our piecewise function, we need to choose the piece where it would be on the left-hand side and right-hand side. So let's look at, let's just look at the graph of it, or we'll just do the left hand. So the limit as x approaches 3 from the left. Now remember, we have already simplified that function. It's just going to be of x plus 3. And then we need to find the limit as x approaches 3 from the right. Again, that function simplified to just x plus 3. So when we're plugging these in, okay, you can choose values that are very, very close to 3. One from the left-hand side, one from the right-hand side. Okay, and then we want to hopefully make sure that they're, you know, about the same value here. We're squeezing in on the same value, kind of visualizing that table from our numeric method. So a number to the left of 3, we could plug in like 2.999, right? That's a number right to the left of it. So we would do like 2.999 plus 3, and we get 5.999. We could do the same idea over here. We could do the number just to the right of 3, so 3.01 plus 3, and we get 6.01. And you can really see that the number squeezed between the two here, or the number that we would get by plugging in 3 to this function, is 6. So our limit as x approaches 3, and we don't have any sort of exponent there because it's just the regular limit of x plus 3 equals 6. So here's our limit. Okay, so we have our function value and we have our limit. Okay, so once you find that your function is defined, you can also find the limit. Our third step is kind of like a conclusion step. So the third thing you need to do is you need to make sure that whatever you found for f of c is also what the limit equaled. So for us, our problem is that our limit was 6 and our function value was 8. So for us, they're not equal, and that's how we can truly say that this is not continuous. Okay, so since for us it was, we had our f of 3, and it was supposed to equal our limit as x is approaching 3, and for us we had 8 and 6, and they did not equal. So what this tells us, since that they don't equal, this is not continuous. This means not continuous. Okay, so our answer would totally be not continuous, and we have a hole at x equals 3, and that's it.